In this video, we'll begin our discussion of section 6.2. This is solutions about an ordinary point. There are something called ordinary points and singular points. There's two different sections in this book about it. We are only going to work on the ordinary points. There in the book, they talk about how to determine if something's an ordinary point or not. We're just going to go with how to solve one of these and not worry too much about the definition of that. But I just want to show you how these series can become solutions to a diffie-q. All right. So it says find two power series solutions of the given diffie about the ordinary point x equals 0. So this is how we're going to start every single time. We're going to make a guess. My guess is going to be n equals 0 to infinity. Luckily, these guesses don't change. It'll be the same thing every time. And c to the n, x to the n. It's like my general form of a power series. Well, this is where it gets a bit tricky. I can now take my derivative of this, right? It's x is our variable. So we're going to get the summation. And I want you guys to just do n equals here. We'll talk about it for in a minute. The n is going to come down times cn. Cn is a constant. And then x to the n minus 1. That's our power rule for monomials. All right, so the n comes down, I get n minus 1. Now, over here, it started at n equals 0. If I do n equals 0 here, you can see that the first term would end up being a 0. So instead of doing n equals 0, we're going to do n equals 1 to infinity. The reason being is because when n was 0, we just got a 0, so we might as well go up. All right, we want to get up to the second derivative. You could tell that these get really bad if we get up to higher powers above 2. They're still bad with 2. So I'm going to do the summation. N equals, let's leave that alone for a moment. I get n times the power comes down, n minus 1, times c, and that's just a constant, x to the n minus 2 now. Now that same thing also applies here. If I leave it 1, this term here will be a 0. So I might as well bring it up to a 2. Okay, so now we have that. What we're going to do now is we are going to come up with our diffie-q expression. Thankfully, there's no single derivative, so that'll help us out just a bit. So y double prime gets me the series n equals 2 to infinity, n times n minus 1 times cn x n minus 2, plus x squared times our guess, our y. N equals 0 to infinity, cn times x to the n. So now what we're going to do is we are going to work that out. One thing I do want to point out, these need to be homogeneous. That is very important here. It would be much harder if they were not. All right, so we have that. And we can go from there, start simplifying things. So I'm going to just rewrite and then bring in that x squared. So you might want to stop for a moment and get caught up there. I'm going to bring in this x squared here. Right? And then if I bring in x squared, this becomes, so I could have left that in, n plus 2. Right? X squared times x to the n is x n plus 2. So now notice this looks like the problems from the last section. So I'm going to need to convert. We'll do k equals n minus 2. That means n is k plus 2. Right? And then here, k equals n plus 2. So that means n is k minus 2. All right, so we're going to switch these to k's. I'll switch to pink here. All right, switching to k's. Okay, I get k equals, this 2 was a 2, so if I plug 2 in for n, 2 minus 2 gets me 0 to infinity. And then I got to plug all these in. Okay, k plus 2 for n minus 1, if I plug in k plus 2, I'm going to get k plus 1, times c to the k plus 2, times x to the k. That was our goal. Right, and then we got to do it on the second one over here. Okay, k would be, if n is 0, then k is 2. And then I get c to the k minus 2, replacing n, and then x to the k. That was our goal. All right, now they both have x sub k's. Now I need to get them to the same index, the beginning number. So I have k equals 0 and k equals 2. I need to let out some from this one. All right, so I'll underline, try to keep things straight. Okay, k equals 0 is going to end up being 0 plus 2, 0 plus 1, times 0, c to the 0 plus 2 times x to the 0. Okay, that was, if we're keeping track here, That was k plus k equals 1 from that one above. If I do k equals 1 now, I get 1 plus 2 times 1 plus 1 times c to the 1 plus 2 times x to the first. Cool. And then we get these series. Again, I'm just going to put it below just for room's sake. Just right here. And now I know, oh, we should underline there, I guess, and show where this term came from. This here was k equals. This was 0, sorry, forgive me. This is k equals 1. Some of you guys were yelling at me back there. And then this becomes k equals 2. All right, now we're good there. So what we did is we let out k equals 0, k equals 1, and then I just rewrote them, put k equals 2. So now we can simplify, put these together. All right, so I'm going to get, if I work all those out, we're going to get 2c2 plus 6c3x plus, okay, and then k equals 2 to infinity, and then I can put these k plus 2 times k plus 1 times c k plus 2 plus c k minus 2, and all that is times x to the k. This is equal to 0. Right? That was homogeneous at the very beginning. Okay, so this is what 6.1 would get up to. What we do from here is you're going to take each place that's in front of, so notice this is a constant, this is in front of x, and then I have the power series. So I'm going to take 2c2, the constants, set it equal to 0. I'm going to take the coefficients of x, set it equal to 0. If there were x squared, I would do that. X to the cube, I'd keep going. And then our last one would be we set the thing that's inside of our x sub k, because I know x sub k will never be 0. So I know that this expression inside the brackets must be 0, because x to the k, the only way that's going to be 0 if x is 0, and that's just our trivial solution. Okay, so this tells us a couple things that are going to help us out. C2 is going to be 0, and C3 is equal to 0. And then the last expression, what you want to do is you're going to always solve for the one, for the C with the higher subscript. So I have a K plus 2 and a K minus 2. I'm going to solve for CK plus 2, right? If I do that, you can see that I would subtract negative CK minus 2, and then I would divide by K plus 2 times K plus 1. Right. Our goal and the book and like my solution manual is going to work out. It'll be the same way. The book takes a different route. They actually pick stuff for C1, C0 and C1. What we want to do is we're going to end up getting everything in terms of C0 and C1. Right. So notice C0 will have, C1 will have, but up here they went ahead and told us that C2 was 0, C3 is 0. So I just needed to work out where I get the next one. So this is for k equals 2, 3, 4, and so forth. You got to figure that out to match up. So C0, and you'll see why C0 and C1 will work out. We'll need those. But then I just need to make sure to hit the list. All right, so I'm going to hit k equals first 2. We are going to run through a whole list of k's here. And you just got to be careful with your arithmetic. All right, if k equals 2, we're plugging it into this. We get 2 plus 2 is 4. So this is C4, right? And then I'm going to get, that's CK minus 2. So if I put 2 in there, I'm going to get minus C0. And then plugging 2 into the number, I'm going to get 4 times 3, which is 12. You're going to see later why I like to write it like this, but I'm going to put it like that. The coefficient was C0, C0. And then I'm just going to keep going up. And there's a way to tell when to stop, and I'll show you. So I get C5. Okay, if I plug in 5 here, 5 minus 3, I'm going to get negative C, or sorry, 5 minus 2 is 3. But notice up here, C3 was 0. I don't even care what this is. This is going to be 0. Okay, so we're good there. Hold on. I think I might have messed up with my yeah, be careful. Okay, so this is a common mistake, and I'm glad I made it here. I plugged in this number here, 5. You got to plug in 3. So this is negative 3 minus 2 is 1. Now it does matter what's on the bottom. This is still C5. So what ended up happening, let me make sure you see my mistake. I put that number into here. That's not what's supposed to go into there. This is supposed to go into there. Okay, I hope you caught on to my mistake there, and maybe you won't make it. The bottom number, if I plug in 3, I get 5 times 4, which is 20. This is going to give me negative 1/20th C1. We're eventually going to get everything down to at least a 0 or something C0 or something C1. All right, so I keep going up. K equals 4. So we get 4 plus 2, that's C6. And you can kind of see in these patterns, they'll start counting up. C0, C1, this will be C2. Now C2 is 0 above, so I'm not even going to calculate the bottom. I know it's 0. I keep going. C5, and you can see the patterns. This goes up to C7. This goes up to negative C3. And then I don't care what the bottom is because I also know that C3 is 0. What I'm looking for, what we really need, what I'd like is for you to go up where you have, when you end up checking these, C0, C1, and then I want you to have 2 more plus the original C0 and C1. You'll see what I mean. So we'll keep going. K equals 6. So I get C8 equals negative C4 over, okay, and then if I plug in 6, I get 8 times 7, which is 56. All right, and that gets me negative 1 over 56 C4. This is why I write it like this. Then I can take negative 1 over 56, and I'm going to replace C4 is negative 1/12 C0. That's going to give me 1 over 672 C0. Right, so I'm putting a check here because I want to make sure I have 4 of these plus the original 2, and you'll see what I mean by the original 2. K equals 7 gets me C9, which is negative C5, over, and then if I plug in 7 into that above, I'm going to get 72. So remember, I'm just plugging back up into here every single time. So I get negative 1 over 72 times C to the C fifth, not 2 to the 5th, C sub 5. Replace C sub 5 with up here, its definition. Negative 1 over 20, C1. This is going to be 1 over 1440, C1. Now, notice I got 4 check marks, and then there's going to be 2 more C0s and C1s, and that'll be good enough for us. We could go up. I think in my notes, I went up to C11. We don't have to, though. I think this was plenty. I went too far in my notes. Okay, so this is how we finish up the problem. I know that my answer, y equals, was the summation of n equals 0 to infinity of Cn x to the n. So what this is C0 plus C1x1 plus C2x squared plus C3x to the third plus C4x to the fourth, and so on. So what we're going to do is we're going to replace every single one of these. So y equals C naught, C0, that's what I'm talking about, the original one. It's sitting there. C1x is going to sit there. And then now I get to start filling things in. All right, so C2 was 0, x squared. C3 was 0 times x to the third. C4 was negative 1/12, C1, x to the fourth. C5 was negative 1/20th. Oh, I put a 0, but it was supposed to be a 1. It was supposed to be a 0 here. So just be careful. This is kind of what I'm talking about. And then negative 1/20th, C1, x to the fifth. Then plus 0 times x to the sixth, plus 0 times x to the seventh, plus 1 over 672 C0 x to the eighth, plus 1 over 1440 C1 x to the ninth, and this goes on forever. So we can now, this is how we're going to get 2 solutions. We are going to pick up all the C naughts and all the C1s. So if I pick up all the C naughts, C0, I get 1 plus, because that would give me times, right? It's got to multiply all the way out. So I get 1, and then I'm going to get minus 1/12 x to the fourth, and then plus 1672 x to the eighth. And then I can give you more. I'll give you a little bit more if you wanted to keep going, just in case you're just like, I want to go further and see if I can figure out how to go further. We're going to get minus 1 over 8, 1, 3, 1, 2, x to the 12th, right? And then this goes on infinitely with a bunch of different numbers. And then C1, I'm going to get x, right? Here's C1. I guess we could have highlighted these maybe to make them easier. C1, 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 and then I'll have one more from my notes to give you. So I got x minus 1/20th, x to the 5th, plus 1 over 1440, x to the 9th. And then the next one, if you want to try to go one more, I got minus 1 over 2, 2, 4, 6, 4, 0, x to the 13th, and on. All right, so your book does, they pick C naught and C1 from early on. I'm just going to do it here now. C naught equals C1, which equals, and I'm just going to call them 1. We could call them whatever we want, but I'm going to just pick ones, and that will make it easier. I just duplicate for me. Sorry, you guys might have to rewrite. And I just get rid of these. There is no constant. So there are my two infinite solutions for this problem. So this is a pain of a process. It takes some practice for sure. I know, and I've taught this class a good handful of times. Um, it has gotten easier with me with time, but really it just comes down to you should identify maybe 3 or 4 um, checkpoints, if you'd want to call them that, right? Figure out, okay, what do I do first? Well, the first thing we did was came up with y. Let's go back and look. We came up with y prime and y double prime. Okay, that's the first thing we're doing. Then we're going to plug it in, and this is that 6.1 stuff, right? We did 6.1 stuff from here down to here, right? So from there to there, that was that 6.1 method. And then here was just plugging in numbers and simplifying and then putting together for our last answer. It's really a way to summarize it. You might want to put a few other checkpoints in there, like, okay, I got it down to this point. Now I do this. I would write it out as you're working through it to help you with the process. It's definitely not a quick one.